Okay.
Yeah, I think it's a good idea to record all these sessions, but
I don't know where it's recording to, but
To your machine, actually.
yes.
When you end your session, do not shut your machine off because it'll start writing to your drive.
Okay. I never shut my machine off, so
Okay, then you're okay.
yeah. Unless I got a Microsoft update. Okay. So a couple of things I'm going to talk about. I wanted to talk about getting colors in narrowband. And I kind of changed the topic a little bit because I'm going to be talking about luminance versus color. So I'm going to show you getting color in color band. I'm also going to be talking about separating your luminance for processing from your color image, so you can bring them back at the end. And I'm also going to talk very briefly about my 3D printing newfound hobby that's now competing with my time. But been making some things for the telescope, so I just wanted to talk a little bit about that. Does anyone else have anything for discussion? And we, of course, we're going to share our latest and greatest.
one thing after seeing Ron's nice image there, I was thinking about is the length of exposures.
Okay.
What's the advantage of going that long compared to, say, 300 minutes or seconds? I think it's a noise thing involved there, isn't it? But
there is a slight noise thing, but my experience is roughly little difference.
And there's always disadvantages to long exposure anyways. Something can happen along the way.
yeah, you mess up one, you messed up a lot of times.
Yeah, and if your sensor isn't got good dynamic range, then you're probably going to burn things too.
But short exposures can suffer from numerical precision too. So you've got more refinement in your numbers, the bigger the numbers are.
Yeah, I guess you just have to rise above the noise floor for sure. I think the guy who wrote SharpCap, he has a little algorithm inside his program, and I think that's what he does. He does measurements, and then he gives you suggestions of what to do.
Okay, so should I start then?
Sure.
I'm gonna try and be quick here. So where's my share of the screen? I don't have a share of the screen. Oh, here we go. Screen 2. Share. Okay, am I sharing?
Yes.
Yep.
Okay. There's the Duncan Clear Sky chart. We'll just put this present. I just only got a couple of slides, so I'm not going to get your math out. So I want to talk just briefly because it's part and parcel of the whole thing of getting your colors right in your color image, your color channels. So, and I just label this divide and conquer, and that is taking your images and well, you probably already are dividing and conquering somewhat. You're likely taking your stars out, so you're dealing with a starless image. So that's exactly what I do with narrowband image. Is I get rid of the stars. I don't want those stars. They're the wrong color. I might use their luminance, but generally I wouldn't. Then I divide and conquer. I get a color and a luminance channel, and I not only do that for SHO or narrowband, I also will do that for RGB quite often, in most of the cases. So the reason you do that is when you take the colors out you're just dealing with the colors. And when you're dealing with just the colors, you're not terribly interested in the details. So signal to noise ratio is only a minor concern when you're dealing with the color image. And you're just trying to get the colors right to show the contrast of this part versus that part. But you can do a lot of noise reduction on the color image. So signal to noise ratio isn't the most important thing. So for RGB, when you get the color image, you would use generally SCC for the stars. And you may bring around the nebulosity with that SCC, but you don't have to. You're free to adjust the colors whatever way you want once you take the stars away. People will expect the stars to be the right color, and SCC generally only changes the star colors. That's the only thing it knows the spectrum about. It doesn't have the spectrum of your nebulosity and how it changes over space. It's just done by interpolation, if you will. It neutralizes the background, and then it takes the stars and just interpolates to what color the galaxy should be. So it's a fine way to do it. But you can also make whatever curve adjustments. If your galaxy doesn't, the blue stars aren't blue enough, feel free to adjust that. If the center isn't color enough, you shouldn't feel encumbered by what SCC tells you about the color of the galaxy itself. It's only its best guess. Of course, if you do have any narrowband channels, we can talk about this. It's another topic about continuum subtraction or continuum extraction from those channels, and then you add it back in. That might be worth a talk on another date. For your narrowband images, generally the RGB will be fairly color balanced. Once you remove the background, it'll be pretty good to begin with. Your background should be fairly neutral. For narrowband, you don't have that option of using SCC. Hopefully, if you do background extraction, the background will be fairly neutral. But what you'll find is typically if you do SHO, that the signal to noise ratio, the signal of the hydrogen alpha, is much stronger than either oxygen or sulfur. Number two is generally either sulfur or oxygen. It can vary, but generally they're dominated by the signal from hydrogen alpha. And if you do an SHO palette, that makes green the dominant color of the image. So what you want to do is stretch or increase the signal of the sulfur and the oxygen channels to meet or exceed that hydrogen alpha. So I'm going to show you basically the ways you do this, either using GHS or Eric Coles, which is the Eric Coles on a pre-stretch, or you can do it a post-stretch. You can use this routine, and I'm going to show you narrowband normalization method. That's what I recommend you use. It's probably the easiest to use and usually gives me great results. There's another facility I'm going to show you briefly called another narrowband color mapper. It's a little more awkward to use, but you've got unlimited freedom to do whatever you want in that. There's the 4X, I can't remember how to spell it, the 4X method that I think Ken, you've used. And then typically you may have to get rid of the green using LRGB combination. That's the way, if you want to get rid of any remaining green, that's my recommendation for use. It gives you better results, I find, than SCNR. Selects it there. And then, of course, if you want to get rid, if you got any magenta, you can get rid of that by inverting, which turns the magenta green. Use SCNR to get rid of the green, and then invert again to get back to normal, and your magenta will be gone. So one thing to note, the color images can be noise reduced a lot. So when you're increasing the contribution of sulfur, of oxygen, not only are you increasing the signal, but you're also increasing the noise associated with those. You're simply multiplying it. So the noise comes up. So in your overall color image, when you adjust the color away from that green dominated version, you're going to see the noise go up a lot. That's okay. You just be heavy-handed on the color noise reduction. So noise reduce that a bit more than you would the other part of divide and conquer, which is the luminance channel. So I am going to touch on this a second. In the luminance, the signal to noise ratio is of major concern, because now you want those details, you want that contrast to be right. You are concerned with signal to noise ratio. So you might steer away, and I'll show you this a second. In either case, for RGB or narrowband, you may steer away what gives you the best signal to noise ratio in order to show something you might want to see. And I'm going to show you an example of that. So for RGB, the highest signal to noise ratio, the best luminance you can get, is probably extracted from your RGB image before you do anything to it, except maybe background extraction. So the only thing I would do with RGB, it's fairly simple. Just check first, right? Or is it showing the details that you want to see? And also consider combining that extraction from the RGB image. If you've got Loom, combine that Loom with whatever you extracted from the RGB image in whatever proportions you seem looks right to make a super Loom. And that will give you the lowest signal to noise ratio. In narrowband, it's a little bit different. The highest signal, and the reason RGB, the luminance or the combined RGB or the luminance channel, especially the combined RGB, is because you're combining all those images and a lot of that background noise is canceling out. In narrowband, it's a little bit different. The highest signal to noise ratio usually comes from the hydrogen alpha channel. If all three channels probably have about the same noise in them, but the signal is much larger in the hydrogen alpha. So it'll give you the bit that needs the least amount of attention. But the lowest noise technically will come from an extraction of your SHO when you combine the channels, because it'll give you the lower noise, but generally the signal of the hydrogen alpha is dominant, so that gives you the best image. But you may want to compromise that. You may not want to just go forward with that best signal to noise ratio. If there's a feature in your image that's not showing in the hydrogen alpha that you want to include, you may not want to use hydrogen alpha as your luminance. You may want to do some linear combination. If there's some feature in the oxygen that you want to capture in your image, you might want to proportion that out. And I'm going to show you that in just a second. Then you can take this luminance and you can do a lot of processes that would just make a mess and show all sorts of artifacts with a color image. But you can go ahead and do that when you've only got the grayscale luminance. and you really focus on bringing out that detail. So then, and you can consider sharpening, and then when you're ready to combine this with your color image, with LRGB combination, you can denoise before or after that combination, and then do some brightness adjustment with GHS. If you're using local histogram equalization, watch for it. It will brighten up parts of your image, probably. But a good rule is to top this out at 85% brightness. If you make the top end of your brightness of your luminance channel higher than this, when you combine it with the color, it'll wash out those high colors and sometimes give you strange things. So if you want to preserve those colors, don't overstretch your image, especially the bright parts. But what you end up with is the best of both worlds, the details from the luminance and the colors from the color image. Then you can make some final adjustments, including stretching saturation, if you will, to make those colors more vivid. That generally you want to do after. So that's it for slides. I just wanted to do a demo of those, couple of those things with the color extraction. So I put together a couple of images. The first thing I wanted to show you was essentially when I did background extraction and put the colors, combined them, and of course in this particular image of the Tulip Nebula and surrounding, as usual, hydrogen alpha was the dominant color. So what you can maybe see a little bit of blue in there, but generally it's green. And so what are we going to do about that? Well, the old way that I used to do it is exactly what I was talking about. Is I would, let me clone that. Is I would just do an initial stretch on that image. And we'll get it there. I'll remove the screen transfer function. And now I got a linear image. And again, the green is dominating quite a bit. So when I look at the histogram for that, you can see I've got the various colors back here, but you can see green is going way ahead of these. And that's why green is dominant in this color. Pixels are generally showing green a lot more than they are red or blue. So the way we could do that is to, and this is the old way, is just first we can start with blue, say, and I can just stretch this. I can just stretch blue. Well, let's show a preview. I can stretch blue, but I gotta curtail it back somewhat to not. Oh, here we go. So I can make blue more competitive with the green, right? So if you see, I just pulled the blue out, trying to maintain the color balance in the background and just stretch that blue out. Okay. So I'll execute that. And then I can do the same for, if I just pick red here. Let's doing the stretch on red. So now I'm stretching the sulfur. So now the sulfur contribution is making the image yellow. But I don't recommend you do it this way. I just did it this way to see what exactly you're doing to change the color of the image. Okay, you're just stretching some of the colors more than the colors to get an overall balance of what's going on. So you might like this or you might hate it. Preview. And so that's the image I took forward. So now we got some of these Hubble golds and blues and stuff that's going on. But I'll park this for a second. But the other way, the way I recommend you use is actually a script called narrowband normalization. But you can figure what it's doing is normalizing is it's adjusting the signal strengths of the red and green, red and blue channels. So it's normalizing all the signals so that they're roughly equal, or the area under them is roughly equal. So that gives you a fairly good white balance. But it's doing more than that. It's doing more than the GHS stretches I did. It's actually making an artificial green color. So it's actually substituting based on the assumption that people don't want a lot of green in their image. And I'll show you how that works. It's actually, for Pixinsight, it's in a process. It's called narrowband normalization. And I'm showing you an SHO image, but it works equally well for an HOO image, an HSO image, or an HOS image, or whatever. Like if you're using a dual band filter, pick the HOO option. But this one happens to be SHO. I'm not going to go through all of them. And let's show the preview. So right off the bat, this is making a really nice color image. So it's actually made an artificial, it's combined the sulfur and hydrogen alpha into a red channel. It's combined all three into a new green channel, and it's combined the hydrogen alpha and oxygen into a new blue channel. And it's made all those contributions the same. It's actually made it, the green's a bit yellow. There is a little bit of green left in here, but not much. There are various options. What I've done is let the lightness be, and it's really not that important, but I've let the lightness be whatever it's calculated to be. So that's what off under lightness. Or I can make the original lightness of the green image preserved, and you get a slightly different hue going on. You can make hydrogen alpha the dominant color. This results in this purpley hue for this image. you really have to take your image by image and see what really works for you. You can do O3, which because the signal's so weak, it's not a very bright channel. Sulfur fares a little bit different in this image, a little bit better in this image, but you can try what you want. You can also make some adjustments here. Oh, I think I like the off one. Oh, maybe the preserve. But if you can add some CNR to get SCNR to get rid of any green. Like if you want to get rid of that green, did you see that happening? When I adjusted this SNR slider. So this is just a matter to taste, right? And you can boost the O3 if you want to boost the blue up a bit. You can boost O3. See how the blue's got a little bit bluer? You can boost sulfur, it'll get a bit redder. It's back. So you can really play with the colors you want. If you find some of the highlights are just a little bit too color saturated and too bright, you can take care of that with some of these factors. It'll tone down the brightest amounts. And if you think the image at all in total is getting too bright, you can adjust that too. So when you're happy, you can put the default stage. When you're happy, you just hit go. And now you've adjusted your color image. In this case, it's still linear, or approximately linear. Technically, it's not linear, but it's close enough. So that's the way I usually, so get this narrowband normalization script, really makes this a piece of cake. The other way, and the reason I'm going to show you this other way, I took the original and modified the original. That was stupid of me. Well, this one will do. The other way, and this is something I normally do anyways, and not for reasons I'll show you later, is to take your color image, or actually before you combine them, if you take the individual channels, you have a red channel that represents your hydrogen, your sulfur. Yeah. So there's the sulfur signal. Here's the O3 signal. And you can actually see there's more noise when it's done the screen transfer stretch. You can see there's more noise in those ones than in the hydrogen alpha or the green channel. Hopefully you can see that across the computer. But this other script is quite interesting. It's called, and it's a script, not a process. It's called narrowband color mapper. So it's a little bit awkward to use, but essentially you start in the middle of the dialog screen, which isn't the greatest way to start, but you pick, let's say, your sulfur channel. And on this color wheel, you're picking the hue. And on this little thing here, you're picking the saturation. So you can have a lot of fun with this, but let's just make sulfur quite, let's make it as red as we can. Right, so there's a line here showing it as red, and I've made it as deep red as I possibly can. And then I say update. And then I want to add a channel, so I click add. It's a bit weird the way it's laid out, but then I'll pick my next channel. You can see it's taken the R away because it's already knows I've used it. But I'm going to take what was the green channel, which was the hydrogen alpha channel. But I don't want to make it green. If I wanted to make it green, I would put it out here. I would like to make it yellow. But you can make it whatever you want. But I'm going to make it yellow. I'm going to give it a high saturation too. And I'm going to say update. So now it's combined the red with the yellow to come up with this, what the image looks like so far. But of course, now yellow is dominant because I've made hydrogen alpha yellow. Then I can just add the blue, and maybe I want to make it maybe a blue in here. Fairly high saturation. And then I'll say update. So what I've done here is I've just redefined, instead of using red, green, and blue, I can redefine whatever color I want to whatever one of my three, and it will combine it together, just like a color combination. Okay, but what I haven't done yet is I haven't balanced out. I haven't done that normalization. I haven't brought the signal of my old R channel and my old blue channel up to that level. And to do that, I know I have to increase the red a little bit here. I can see I have to increase the red. I go to this next panel down, and I click on the red and I say edit. And this histogram, now I'm doing a little bit of a histogram stretch. This part's a little awkward. If you can think of the histogram transform with that slider at 0.5, what you want to do is move that slider to the left, but there is no slider in this. At least they haven't put one in yet. But if I move that slider to the left all the way 0.1, you know I'll be moving the histogram, I'll be stretching the red. So it stretches the red, and now you see that the red is competing with the yellow because I've stretched the red up. Okay, it doesn't make sense that I'm lowering this midtones number to increase. It's trying to get people to understand the equations involved, and they don't quite. But so when I'm happy, let's say I'm happy there, I can update. I also want to stretch the blue a little bit, so I'm going to pick the third channel and say edit that. And I want to increase the blue. Maybe I want to try it the same amount. Would I make the other one 0.1? So I'm stretching I stretched the blue a little bit more than I did the hydrogen alpha. And there's my result there. I can add a little bit more blue maybe. So make this 107 maybe. A little bit more blue in there now. You see some blue in this area. And then, of course, when I'm happy, I can say update. Don't forget to say update. And then I can say, generally when I'm done, I want to make sure that the background is neutralized. So I can do a bit of background neutralization here if I want. Well, I guess I was doing it all along. And then I don't want to output my colorize. I'm just going to apply an STF to the output image. Say okay, and it'll basically do what I told it to do. Now on your own, I suggest it's set up so that you can try different colors, try different saturations when you add these things together. Ooh, that came out quite purple. I guess I did increase that blue too much. But anyways, it's kind of interesting to play with, but it's awkward. But it gives you all this freedom. I would go back and I would adjust that blue again. And I exited the thing, but I don't think you necessarily need to. But there's our three color. Here's the original color. Here's what I just did. Here's my stretched image. And where is my... That's the one I did with GHS. Oh, here we go. That's that one. Did I not? Is it? I must have got rid of it. Oh, here's my narrowband normalization. So one of those methods should appease you. Work with it. I didn't show the 4-ax method. It's another way of doing the same thing. But essentially, that's what you're doing in all these three things, is you're boosting the other channels to match. Now, is this noisy because I boosted two of the channels? Maybe a little bit. I haven't done any noise reduction on any of this, but that's fine. Okay, you'll get noise reduction later, and it'll be just hunky-dory. Okay, I did want to quickly talk about going back to our green image.
Dave, before you do that, I notice you're kind of adjusting the levels of each of the filters. When you shot this, did you shoot all the filters at the same exposure in the narrowband?
Yes, I did. All the same
Okay.
exposure and same number of frames.
Mm-hmm.
Now, I'm going to put that question, if you could just park it for a second, because I'm going to show you something now that has everything to do with that, right? So if you recall, these are the green, red, and blue channels that I extracted before. There's one more thing I want to extract from this, and that's the luminance channel. Okay. So I happen to know, because, and it was something I was after when I was doing the tulip nebula, that right over here on this side of the tulip, there's a bow front associated with bow front associated with sigma X1, giving off these X-rays. And you can see in this image, it's very, very faint. And but it's blue color. So it's dominating in oxygen. Now I can confirm that. I can look at, let's look at the R channel, which is the hydrogen alpha, which is the sulfur, and you can barely make it out here, right? If I look at my green channel, yeah, it's there. It's a bit stronger than in my, stronger than in my red sulfur channel. And then if I look at blue, which is O3, I can see, oh, it's pretty strong, especially relative to everything else in the blue channel. So one thing I do is I either re-extract the color channels, and if there's something you want to see, take a look at them. If I normally just want to, you must normally want to forge ahead and use your highest signal to noise ratio image to make your luminance. And that might be your hydrogen alpha. If there are, but there may be some features that are missing in hydrogen alpha that do appear in your combined extracted luminance, right? So what I did do is make a little pixel math routine that just takes my 4 candidates to be my luminance. There's my extracted luminance from all 3 color channels. There's my red channel, my green channel, and my blue channel representing sulfur, hydrogen alpha, and oxygen. So in this base model, you can see I take the luminance extract and multiply it by 1, and then I take the red, green, and blue, multiply them all by 0. So when I do that, I just basically get the luminance back again. Oop, failed. No such image. Oh, because I didn't use the same one. Let me extract these. Well, I've modified it now, but that's okay. The point's the same. I'll really make the point in just 1 minute. So here's my RGB and L channels. There's what my L looks like, right? I got that faint bow front. But if I use a different, if I apply this, I just get the L channel back because it's only 1 multiplied by 1. So that's my extracted lume 1. But here I'm going to extract the lume a little bit differently. This time I'm going to take 40%, multiply it by 0.4 of my luminance, my extracted luminance, and take 30% each of my red. Sorry, I don't want to take any red. I want to take my hydrogen alpha and my green. So I'm really taking an extracted luminance that's weighted towards hydrogen alpha because I like its signal to noise ratio, and it's got a lot of the nebulosity in it. And I'm also weighting it towards the blue channel, which has my Cygnus X1 bow front. So when I do that one, hopefully you see that I've made that bow front a little bit more dominant in the right image than in the lesson. And So if there's something you want to bring out, look at what color channel, when you're creating a luminance file, look what channel it might be showing up in more. Now I'm paying for that with a little bit higher signal to noise ratio now, but I would be very disappointed if it didn't come through at all. And I'm just going to show you one example of doing that same thing. It's a more extreme example. And it's one I'm still working on. I created an image of, this is through my Antlia tri-band filter. And you can barely see it, firstly because of all the stars, but it's basically a mosaic of spaghetti nebula. So here's what it looks like when I remove all the stars. And now, granted, I need more frames, and that's one of the things I'm doing tonight is getting more frames for this. But you start to see that structure. And when you look closely at it, it's a very, very dim SNR. And it's got some parts that are green, just like the Cygnus loop. It's got some filaments that are green that aren't very visible at all. Most of the filaments, strong filaments, are in that hydrogen alpha channel. So I don't need to do any color adjustment. I'm fine with the colors. You can see some blue coming through, halos of some stars, and there's some artifacts because I messed up on my flat files. There's lots of things wrong with this image. But when I extract the various colors, when I extract the channels from this, you can see in the O3, you can see some of the fainter O3 strands in there. When it comes to, oh, sorry, I'm getting mixed up. The blue is a broadband catcher. So the O3 comes through in blue with a one-shot color camera and a tri-band filter. You can see a lot of this parts that's heavy duty O3 is coming through in this image. It's barely coming through at all in the blue. And most of the strands are in the red image, right? So if I took a luminance of my original color and went to work with that, you can see, yeah, okay, I can see the nebula just like I could in the color one, but it's not that strong. But if instead I create the same thing here, except now I'm going to weight the results. I want 60% of my luminance to be just the R channel, which is the hydrogen alpha. And I'm going to make 40% of it that green channel. I'm not going to include any blue in my luminance whatsoever. At most, it's a little bit of a halo around some of the stars, which I may not want anyways. So I'm going to leave blue totally out of my luminance. And then when I do that, you can see in my linear image, I'm getting the nebulosity just come out a lot stronger than if I had just said, give me the lume. Now, a lot of times just give me the lume would be fine if you've got a good balance in your color channels to begin with. But on something like this, where the main feature I want to bring out it's great to start with the main feature that represents what I want to look at. So that's one of the strongest things about doing the narrowband, but you can also do it with RGB, is if there are things that you want to be stronger, build your luminance. It doesn't have to correspond to your color. So later on, you'll here is that same nonlinear nebulosity after I brought out a bunch of the details, right? And that's what I do use to combine with my ultimate color image, which basically looks like that. So I can, I don't know if you do a lot of LRGB combination, but I can, I don't know if I have a stretched one here. Let me quickly stretch this so you can see I'm not lying. Here, stretch that. Oh, it's not HDMT, it's histogram transform. Here, here, like that to this. Screen transform. Then I'll take this luminance that I worked so hard to create, and I'll say, use this LRGB combination. I'm going to apply it to the color image so I can click these off. Just click. This is this image. And skip the chrominance noise reduction, which I normally wouldn't, but just apply that luminance to this color image. And you see the color of the luminance will bring the details that the color image isn't showing, but it'll adopt the colors of the color image. Right? So then I might have to adjust the saturation of that. Just the GHS. Resulting histogram looks like. Of course, I would take a lot more care if I was doing this, but let me just check that to saturation. And so I didn't do anything to the colors other than just stretch it. But when I did this for myself, here's the result I got. I boosted the green a little bit in there to get some of that nebulosity. So it's a pretty dirty image. And then I add back in the stars. And that's kind of where I left it, but I have to go back, and you can see the signal's pretty weak in here, and looks pretty dirty. I maybe should darken it up a little bit, but anyways, that's how that works. Chicks, for kicks and giggles, we can take that. Oh, that's. Let's put it back to where it was. Here's where it was. If I go to narrowband normalization, this is essentially an HLO image. You're not doing much.
You need the preview window on.
Oh, that's what I do. Thanks. Now I gotta undo everything I did. So it gave me a yellow color. So changing your colors is pretty simple.
I think that was absolutely fascinating, Dave. Thank you very much.
Well, hopefully it's helpful.
Yeah,
So-
that narrowband normalization, if the guys are looking for it, it's a Bill Blanchard script.
Do you have to go to his website, Ken?
Oh, no, the one to go through is cosmicphotons.com.
Okay.
So the guy who I wrote GHS with teamed up with Bill Blanchard to create that script. It's a lot slicker because I think Bill Blanchard had a lot to do with it. And then the other one, the awkward one, but I think is more versatile at the end, is Adam Block. With that one.
Oh, is that Adam Block's routine? The mapper?
Well, it was kind of Adam Block's idea. It was Mike Cranfield's routine.
Oh.
But I don't think Adam had all that, other than the original idea. I don't think he had much to do with it.
David, you said that you might be able to answer the question about increased exposures during
Yes.
exposure.
So it goes back to when you're creating your loom, if you know that, say, the object you're after shows up in oxygen strongly, right? But so you know you're going to use oxygen in your luminance. You should take more integration time on your oxygen, because that way you're going to boost its signal to noise ratio.
So not necessarily exposure time, but just more frames.
Your total integration time, which is your number of frames times your exposure time.
So you can do it either way. You could use longer,
Do it either way.
or use more frames.
Either way.
Okay.
Okay. It's your total integration time that really matters.
Yeah.
How much time are you letting photons hit the sensor?
So that's an alternative to doing the pixel math if you know you want that channel anyways.
Yeah.
So ahead of time.
If you're going to use hydrogen alpha as your luminance, and you're just going to use the O signal and the sulfur signal for color, well, it doesn't need to have the same signal to noise ratio because you're not using them in your luminance. If you're going to use it for luminance, its signal strength is probably not going to be as strong as the hydrogen alpha. So you might want to take, in the case of the bow front, you might want to take more oxygen data. And that way you're both. A really good example is that the squid, right? The squid and the flying bat. You know the nebula I'm talking about?
Yep.
Yes.
So if you just take the same amount of hydrogen alpha and O3, that squid is very, very weak signal compared to the flying bat in the background. So if you just take the same exposures of each and don't normalize, that squid is going to be very, very, very faint. So if you want it to come through, you either have to stretch it more, which a lot of people do, but when you stretch it more, you're also stretching all the noise.
Yeah. So
Right.
ideally, it'd be better to have integration signal rather than stretching.
Right. So really you should, if I was to shoot that today, I'd probably take 3 oxygen frames for every hydrogen alpha frame. And then their signal noise ratios might be more comparable. And you'll end up with a crisper, cleaner image at the end of the day.
Yeah, I guess the more you know about the subject, the better prepared you are. I guess if you don't really know, then equal all the way across.
Yeah. Well, in a lot of cases, hydrogen alpha is going to be your luminance. Or just the extracted luminance, which is an equal weighting of the 3 colors. Right.
And so all you need is like a couple of frames of each one, and you can tell.
Well, the interesting thing is I didn't get into this when you're doing stars. The signal on the stars is so strong. You don't need many RGB stars, even if the nebulosity looks like hell in your RGB image. You don't need much star data in order to make really good stars.
So do you do separate RGB?
I lost you, Dave. I didn't hit any buttons. Is anyone there? Or is it me? I'm afraid to exit and lose the recording.